2.5 Succinct representations of games. Computational problems have inputs, and the input to Nash is a description of the game for which we need to find an equilibrium. How long is such a description? Describing a game in a strategic form entails us listing all utilities for all players and strategic combinations. In the case of two players with M and N strategies respectively, this amounts to describing two M and numbers. This makes the two-player case of Nash such a very neat and interesting computational problem. But we are interested in games because we think that they can model the internet, markets, auctions, and that these have far more than two players. Suppose that we have a game with n players and think of n as being in the hundreds or thousands, a rather modest range for the contexts and applications outlined above. Suppose for simplicity that they all have the same number of strategies. Call it S. In any non-trivial game, S will be at least 2. Representing the game now require n times S to the n numbers. This is a huge input. No user can be expected to supply it, and no algorithm to handle it. Furthermore, the astronomical input trivializes complexity. If S is a small number, such as 2 or 5, a trivial efficient algorithm exists. Try all combinations of supports. But this algorithm is efficient only because the input is so huge. For fixed S, 2 to the S to the n is polynomial in the length of the input, n times S to the n. Conclusion. In our study of the complexity of computational problems, for games such as Nash, we must be especially interested in games with many players. However, only succinctly representable multiplayer games can be of relevance and computational interest. And there are many such games in the literature. We start by describing one of the latest arrivals, Kearns et al. 2001, that happens to play a central role in our story. 2.5.1 Graphical Games. Suppose that many players are engaged in a complex game, yet the utility of each player depends on the actions of very few other players. That is, there is a directed graph 1, 2, 3 until n and h set E with vertices the set of players and ij in E only if the utility of J depends on the strategy chosen by I. J's utility depends, of course, on the strategy chosen by J. More formally, for any two strategy profiles S and S prime, if Sj equals to Sj prime, and for all ij in E we have Si equals to Si prime, then uj of S equals to uj of S prime. A graphical game, as these are called, played on a graph with n nodes and integrate at most d, and S choices per player requires only n times S to the d plus 1 numbers for its description. A huge savings over n times S to the n when d is modest. For more on graphical games, see Chapter 7. For a simple example, consider a directed cycle on 20 players where the utilities are captured by the game matrix A of example 2.2. That is, if a player chooses a strategy I in 1 to 3 and his predecessors in the cycle chooses another strategy J, then the utility of the first player is Cij. The utility of the predecessor will depend on the strategy played by his predecessor. Ordinarily, this game would require 20 times 3 to the 20 numbers to be described. Its graph structure reduces this to just a few bytes. Can you find the Nash equivalent in this game? Other succinct games. There are many other computationally meaningful ways of representing some interesting games succinctly. Here are some of the most important ones. 1. Sparse games. If very few of the n times s to the n utilities are non-zero, then the input can be meaningfully small. Graphical games can be seen as a special case of sparse games in which the sparsity pattern is captured by a graph whose vertices are the players. 2. Symmetric games. In a symmetric game, the players are all identical. So, in evaluating the utility of a combination of strategies, what matters is how many of the n players play each of the s strategies. Thus, to describe such a game, we need only s times n plus s minus 1 choose s minus 1 numbers. 3. Anonymous games. This is a generalization of symmetric games in which each player is different but cannot distinguish between the others, and so again, his or her utility depends on the partition of the other players into strategies. S times n plus s minus 1 choose s minus 1 numbers suffice here. 4. Extensive form games. These are given as explicit game trees. See the next chapter. A strategy for a player is a combination of strategies, one for each vertex in the game tree information set. More accurately, see the next chapter for details, in which the player has the initiative. The utility of a strategy combination is that of the leaf reached if the strategy are followed. 5. Congestion games. These games abstract the network congestion games studied in chapters 18 and 19. Suppose that there are n players and a set of ages is E. The set of strategies for each player is a set of subsets of E called paths. For each age E in E, we have a congestion function CE mapping 0, 1, 2, 3 until n to the non-negative integers. If the n players choose strategies paths p equals to pi until pn, let the load of HE L of p be the size of the set. That is the set of index I such that E in pi. Then, the utility of the ith player is the summations of CE of L of P, summing for all those E in Pi. There is an even more succinct form of network congestion games, where E is the set of addresses on an actual graph, and we are given two vertices for each player. The strategies available to a player are all simple paths between these two nodes. 7. Local effect games. These are generalizations of the congestion games. See Layton, Brown, and Tannerhouse, 2003. 8. Facility location games. See Chapter 19. 9. Multimetric games. Suppose that we have m players with m strategies each, and for each pair ij of players and m by m utility metric aij, the utility of player I for the strategy combination S1, S2, S3 until Sn is the summations of A with a footnote Si, Sj to the ij, summing for all those j not equals to I. That is, each player receives the total sum of his or her interaction with all other players.